Assalamu alaikum. Hope you are doing fine. We have learned about Gauss Law. In this video, we are going to use Gauss Law to get the electric field due to an infinite long charged wire. For that, I considered this one as infinite long wire that carries positive charge. Here, this wire is said to have uniform linear charge density represented by letter lambda. Lambda stands for linear charge density. And what is this linear charge density? It is nothing but the charge enclosed for a given length. In simple words, charge per unit length is nothing but linear charge density. How many charges are present in a given length of the conductor is referred as linear charge density. Now, I take a point P at some perpendicular distance r from the charged wire. Then I choose two charged elements A1 and A2 at equal distance from point P. To show that, in order to show that this point is at equal distance from A1 and A2, I am going to connect this points to P. And the same thing I do here as well. So this clearly shows that P is at equal distance from A1 and A2. Then by taking this perpendicular distance as a radius, I draw a circle. Draw a circle here. Okay. This circle have radius r. So it's nothing but the perpendicular distance. As I have told you earlier, this wire carries positive charge. We know the electric field due to positive charge carries the electric field lines projecting outwards. So this also have this positive charged wire also have electric field in which electric field lines are projecting outward. Here this arrow mark represents the direction of electric field. So if we take any point on this circle of radius r, you will find the value of E remains the same. So we can say that here is constant. So from this, one thing is clear that this is a charged wire possesses a cylindrical symmetry. So, if we want to apply Gauss law to get electric field, then we can take a Gaussian surface which is cylindrical in shape. So, I draw the same figure here. This is the wire of infinite length carrying positive charge. Carrying positive charge. Then to apply Gauss law, I take a Gaussian surface which is in the form of a cylinder. This Gaussian surface is in the form of cylinder. What is this? Gaussian surface. Then, as I told you earlier, here the electric field is projecting outwards. Then we know the expression for electric flux 5E, which is nothing but closed integral of E vector dot dA vector. Here E is electric field and dA vector is the direction of area elements. Now, to make our work easy, I take 3 area elements on this Gaussian surface. I take one area element here, one here, and this is a curved surface. Then another area element is taken on the top of this cylinder, and third one is taken on the bottom. In all these 3 cases, the electric field is projecting outward. Now, represent letter E vector. The same here as well, vector, and here also it is E vector. Whereas the direction of this area element is given by dA vector, and it can be obtained by drawing a normal. This normal is n cap, which actually represents the direction of dA vector. Here dA is the area element. The same here as well, dA. Okay. It's d A. Now that is a d A for this one. And we follow the same method here as well. We draw a normal n cap, which represents the direction of the area element dA. This dA vector. And the same here, n cap. This represents the direction of this area element. It is a dA vector. And if you observe them keenly, you may find the angle, the angle between E vector and dA vector in this case is 90 degree. So theta is equal to 90 degree here, and the same thing here as well. Theta is equal to 90 degree. Whereas here the angle between E vector and dA vector is 0 degree. So I am going to expand this. Now if you look at this carefully, you will find here I have taken closed integral. This stands for the closed surface. So when I expand this, here I take these 3 area elements. Now 5E is written as line integral of E vector dot dA vector for curved surface. Curved surface plus line integral of E vector dot dA vector for top surface plus line integral of E vector dot dA vector for bottom surface. So The sum of these three provides us closed integral of E vector dot dA vector, which in turn gives us the electric flux. Now, we know one thing. A vector dot B vector, this dot product of vectors, can be expanded as A B cos theta. Now, the same method we can follow here. Instead of say E vector dot dA vector, we can write E dA cos theta. Okay, this I am going to use here in this equation. So what do I get? I get this 5E equals to line integral of E dA cos theta. What is the value of theta for curved surface? It is 0. So cos 0 degree. This is for curved surface. Curved surface plus line integral of E dA for top surface. For top surface, theta value is 90 degree. So cos 90 degree plus line integral of E dA cos of 90 for bottom surface. Bottom surface. Now, we know very well cos of 0 is nothing but 1, whereas cos of 90 is 0. So, the entire term becomes 0, whereas here it is written in this manner. 5E is equal to integral of E dA multiplied with the 1. Multiplied with the 1. Okay, and this becomes 0. We know when we multiply something with 0, the result is 0. Same here. So, only one term is left, which stands for curved surface. So, we need to mention that. I'll leave it as such. Then 5E is equal to integral of E dA. Here I told earlier E is a constant. We cannot integrate a constant term. So it is taken outside. So 5E is written as E integral of dA. We know when we integrate dx, what we obtain is x. The similar way, if I integrate dA, I will get A. So here it is a differential part. When we integrate a differential part, the differentiation get cancelled and we get this. Yeah. Okay. So by following that, what do you get? 5E is equal to E dot A. Here A is the total area of the curved surface. What is this? Here A is the total area of curved surface. A is total area of curved surface. Of what? Of this cylinder. Okay. So it is represented as A is equal to 2 pi RL. This is the area of the curved surface of this cylinder. So in the place of this I write 2 pi RL. What is this L? Here L is the length of this cylinder and R is its radius. This R. I hope you have understood. Now we are very close to get the value of E. Our aim is to get the electric field due to this charge carrying infinite long wire. 5E is a E 2 pi r L. And what is this 5E here? 5E is nothing but electric flux. To get its value, I apply Gauss Law that will ultimately provide us the expression for E. So applying Gauss Law. What is Gauss Law? Gauss Law says that electric flux is equal to the ratio of enclosed charge and permittivity of free space. So what is this enclosed charge? To get this, I use this expression. We know lambda is equal to Q upon L. So from this, enclosed charge is obtained by cross multiplication, lambda into L. No, this I am going to use here. You see what I get if I do so? 5E is equal to lambda L upon epsilon naught. This I am going to use in the above equation. Here, I'll use here. So what I'll get? In the place of 5E, I write this. E 2 pi r L equals to lambda L upon epsilon naught. Now our aim is to get the expression for E. So I keep E this side and remaining terms are taken to right hand side. I get this equation. E is equal to one upon 2 pi r L into lambda L upon epsilon naught. Here similar terms get cancelled. L and L get cancelled. And what remains here is nothing but this. E is equal to 1 upon 2 pi epsilon naught lambda upon r. This is the final expression that provides us electric field due to an infinite long charge carrying wire. In vector form, this can be written as E vector equals to 1 upon 2 pi epsilon naught lambda upon r into r cap. Here r cap is the unit vector which provides the direction to this part. Now one thing you need to know about this: when the charges are positive in the wire, the electric field acts outwards. So R is positive. When the wire is provided with a negative charge, then the electric field will act towards the wire, and here we will use a minus sign along with R. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.